We will continue our discussion on Chapter 11 with percent yield. Up to now, we have used stoichiometry and stoichiometry methods to calculate amounts of products. Those calculated amounts we call theoretical yields. Those are the maximum amount of product that can be formed theoretically. It's the maximum obtainable yield that we can get from the balanced equation. However, the amount of product that is actually made in the laboratory is less than the theoretical yield. We call that amount the actual yield, and we typically weigh that or calculate it by other means, not necessarily stoichiometry. So there are reasons why the actual yield is smaller than the theoretical yield. We might have competing reactions, or we just aren't very good at collecting all of the product that is made. Whatever the reason, the actual yield typically is less than the theoretical yield, but never more. We determine how efficient a reaction is by calculating the percent yield, which is given to us by this formula, and it really looks just like a mass percent that we have already discussed. So the percent yield is the actual yield divided by the theoretical yield times 100. Note that this is less than 100%. If you get over 100%, it might mean that you have flipped these two numbers, or that you haven't calculated the theoretical yield correctly. So go back and figure it out if you've made an error somehow. If everything looks fine, then that means that our actual yield is not correct, because sometimes there might be impurities, or we've collected other things other than the product that we really wanted. So there are impurities in there with that product. Let's take a look at an example problem. We have PCl5 decomposing to give me PCl3 and Cl2 according to this reaction. First thing you have to do is figure out if it's balanced, and it is. Then the problem tells us determine the percent yield if 3.45 grams of PCl5 decomposes to yield 2.1 grams of PCl3. Note two things. You are given an amount of PCl3 in the problem, which tells me that that is the actual yield. If the problem already tells you how much product you collected, that's your actual yield. We also have an amount of grams of my reactant, and I can take this and use those stoichiometry methods that we have been using up to now to calculate theoretically how much product I would be making if all of that 3.45 grams was used up. This amount is given to me in grams, but I can't convert grams of PCl5 to moles of PCl3 directly. I can only work from the balanced chemical reaction. I can only go from moles of one to moles of another. So the first step would be to convert this amount from grams to moles. Here is my reaction again, just so I have it visually there. And here we go. I start with the amount of reactant that was given to me and convert from grams of that to moles using the molar mass of PCl5. I divide by the molar mass, so 3.45 grams divided by 208.2 grams per mole gives you 0.01657 moles. Note that it's a 1-to-1 ratio. That means that whatever amount I have of PCl5, it's going to be the same amount of PCl3 formed, theoretically. Now that I know that I have this much PCl3 that will form, I can convert this to grams using the molar mass of PCl3. And here's the last step. I take the moles of PCl3 multiplied by the molar mass this time, because I'm going from moles to grams, to give me 2.275 grams of PCl3. Note that this amount is larger than the amount that was given to me in the problem, which means that this is the theoretical yield. I am calculating it. That's theoretical. What was given to me in the problem is the actual. Lastly, I can take the amount, the actual yield, 2.1 grams, divided by 2.275 grams times 100 to give me 92.3% yield. And it's less than 100%, so it's pretty good. If this were over 100%, I would take a look and see if I had these two numbers flipped. If they weren't flipped, then I would go back and figure out if I made a calculation mistake in my theoretical yield. Let's take a look at one more problem before you try your hand at doing one of these. I have aspirin that is formed from salicylic acid and acetic anhydride. And note that I could walk you through it, but just convince yourself this is a balanced chemical reaction. And it's a 1 to 1 to 1 to 1 ratio. So it's pretty simple. Whatever amounts I have of reactants are going to give me the same amounts of product. Now, in a certain aspirin synthesis, 104.8 grams of salicylic acid and 102.3 grams of acetic anhydride are combined together. Calculate the percent yield if 105.6 grams of aspirin are produced or collected. So note two things. This amount here is going to be the actual yield because it's given to me already in the problem. This is the amount of product that is produced, and the problem tells me that. So that's actual yield. Now, the second thing I need to do is calculate the theoretical yield to be able to calculate the percent. How do I do the theoretical yield? I calculate it by the amount of reactant that I'm given. Note another thing. I have two amounts given to me for each reactant. We said in the previous video that if you have two amounts of reactants given, so amounts in grams or moles for both reactants, you will have, you got it, a limiting reactant problem as well. So I need to figure out which one of these is going to run out faster and how much product that is going to make. That's going to be my theoretical yield. I do that by converting these amounts to moles first and figuring out how many moles of product I'm going to make from that. Then I will use the least amount of product to convert back to grams of product and compare it to this actual yield. Let's take a look. Here's my reaction, and it's a 1 to 1 to 1 to 1 ratio. Keep that in mind. I first start by taking the amount of each reactant and converting it to moles. So I take 104.8 grams of my salicylic acid and divide it by 138.12 gram per mole, which is the molar mass of salicylic acid. I divide by that molar mass when I go from grams to moles. And this is how many moles I would get, 0.7588 moles of salicylic acid, salicylic acid. Then I do the same thing for acetic anhydride. I take 102.3 grams, divide by its molar mass to give me 1.002 moles of acetic anhydride. Now, because I have a 1 to 1 ratio for all of these, if I had 0.7588 moles of salicylic acid, I would be making the same amount of my aspirin, 0.7588 moles, because it's a 1 to 1 ratio. If I had 1.002 moles of acetic anhydride, I would be making the same amount of aspirin, 1.002 moles. Note that because I have fewer moles of salicylic acid, this is going to be my limiting reactant. So this is how many moles of salicylic acid I'm going to be making. Then I can take that and multiply it by its molar mass to give me how many grams of acetylsalicylic acid or aspirin I'm going to be making. So I have 0.7588 moles of aspirin multiplied by its molar mass now, because I'm going from moles to grams, and I multiply by the molar mass to give me 136.7 grams of aspirin. Note that this is a larger amount than 105.6 that I was given in the problem. Now, this is my theoretical yield. I can compare it to my actual yield to get the percent. And here it is, percent yield, 105.6 grams, which is the amount from the problem, divided by 136.7, which is the amount that I calculated, times 100 gives me 77.25%. And I've done it correctly because this is less than 100%. Here is a problem for you to try. Ammonia is produced by the reaction of nitrogen and hydrogen. Determine the percent yield of ammonia produced when 35 grams of nitrogen react with 12.5 grams of hydrogen. The actual yield is 31.6 grams. So this is your actual yield. You have a limiting reagent problem. So figure out how much product you're going to make from 35 grams, how much product you're going to make from 12.5 grams. The one that's giving you the smallest amount, that is going to be the theoretical yield, and then use the actual yield and the theoretical yield to calculate the percent yield.